This is the third lecture on elements of semi-classical gravity. In this lecture, I will first talk about thermodynamics of black holes. I will very briefly describe how black holes form, and I will just briefly mention how one was led to the laws of black hole thermodynamics, how there arose a puzzle, particularly prior to the discovery of Hawking radiation, how black holes seem to have entropy but no temperature, and how Hawking radiation sort of resolved this puzzle. And Hawking radiation corresponds to production of particles by a collapsing black hole. And interestingly, what one finds is that once this collapsing matter collapses into the Schwarzschild horizon, the particles that are observed asymptotically at late times far from the black hole have a thermal spectrum. And this thermal spectrum and this temperature associated with the thermal spectrum fits in nicely with these laws of black hole thermodynamics, resolving some of the puzzles that had existed prior to that. There is something interesting that happens when one studies Hawking radiation. What you need to do is that you need to impose the initial conditions of the modes at very early times. The picture one has is a collapsing black hole, a collapsing object that eventually collapses to form a black hole. So you are considering quantum fields around it, and as I have been repeatedly talking, the behavior of the quantum field is determined by the behavior of the modes, classical modes. And what you have are classical modes that will, where they will be spherically symmetric, and you will impose initial conditions on these modes and therefore on the quantum field at very early times when you had a very large descended object, and therefore the gravitational field is very weak outside and therefore very close to the Minkowski vacuum. And the object collapses, eventually forming a black hole. The modes, will evolve, and you are looking at the behavior of the modes, as observed by an observer far away from this black hole at very late times. And what you find is that as you track back a typical mode, like if you have a black body spectrum, you know where the maximum of the intensity is going to be, is determined by Wien's law. So you have a typical wavelength associated with these modes, and you track back the mode and ask what is the frequency of the modes at very early times, you will find that the frequencies are very large. Or equivalently, if you ask what is the corresponding wavelength, they are smaller than the Planck length. And that is when you impose the initial conditions on the mode at very early times. And then you are left wondering whether quantum gravitational effects will modify Hawking radiation. Something similar happens when you study inflation. You take a mode today, cosmological scale today, and you track it back and ask what is the wavelength of the mode at very early times. And you will find the following. I will explicitly show this number. Roughly the duration or the change in the scale factor from today to the end of inflation, and you assume about 60 or 70 e-folds of inflation. 70 is being generous, but let us assume so, and ask what will be the wavelength of a mode which corresponds to, say, a few megaparsec. You will find that at the start of inflation, not quite the start, 70 e-folds from the end of inflation, the wavelength of the mode will be of the order of the Planck length or smaller. And this leaves you with a question as to whether Planck scale effects can modify your primordial spectrum. and this is known as the Trans-Planckian problem. The Trans-Planckian problem was originally discussed in the context of black holes for reasons I mentioned earlier. It is easier to discuss in the context of inflation. So what I am going to do is that I am going to just highlight the problem. This problem in the context of black holes was well known. It appears in Wall's text, for instance, and it was recognized in the early 2000s. The Trans-Planckian problem occurs in inflation as well, and I will discuss how one tries to understand the Trans-Planckian problem in inflation. The difficulty primarily is that you want to take into account Planck scale effects, which are supposedly quantum gravitational effects, and we do not have a viable working quantum theory of gravity. So you need to construct reasonable arguments to understand what are the implications, what are the possible imprints of Planck scale physics on, for instance, the primordial power spectrum. And then I will just briefly summarize. So let us start with the thermodynamics of black holes. I am going to make some very generic remarks about how black holes are formed, why you need general relativity, what are the successes of classical tests of general relativity, and then the behavior of space-time around black holes, and then I will go on to discuss black hole thermodynamics and Hawking radiation. I presume all of you will know the life cycle of a sun. Stars are born due to collapse of large gas clouds, and they evolve over billions of years, and our sun in particular is supposed to evolve into a red giant. We are somewhere here a few billion years. Okay, I am sorry, we are here at a few billion years, 4 to 5 billion years, and eventually it will evolve into a red giant, and these are closely related to the process that fusion process that happens inside the sun. Hydrogen burning stops, helium burning starts, etc., and then it can eventually behave like a red giant. It can throw out on matter on the surface. It can eventually this will be seen as a planetary nebula, while the core will go on to become a white dwarf. Now we discussed this part as to how an average star such as the sun goes on to become a white dwarf. If the massive star, if the mass of the initial gas cloud is extremely large, it can end up as a neutron star or as a black hole. It will end up as a black hole because in the case of white dwarfs, you have essentially the electron degeneracy pressure that supports against gravity. In neutron stars, it is the neutron degeneracy pressure that stops gravity from collapsing it completely. But if the initial mass of the star is very high, even this neutron degeneracy pressure is inadequate, and you end up forming a black hole. And such objects have to be described by general relativity, and you are aware of flat space-time where world lines are straight lines essentially, and the space-time is flat in the absence of any matter, and light cones behave in this simple fashion that you are all familiar with. They are in 45 degrees, assuming c equal to 1, and this is the future light cone and this is the past light cone. The moment you throw in matter, the light cones, the behavior of the light cones change, and black holes are extreme cases where the future light cone is directed towards the center of the black hole at the event horizon, and therefore light can't even escape. And this is what matter does. It curves your world lines. You can think of space-time as a rubber sheet, and the placing the matter alters the geometry of this rubber sheet, and as is the as the famous quote due to Wheeler, matter tells space-time how to curve and space-time tells matter how to move. And general relativity is well tested. I presume all of you are familiar with these classic tests of general relativity. It is able to explain the precession of the perihelion of Mercury. It is able to explain gravitational bending of light in the context of cosmology. This is, or astrophysics, this is constantly observed. This is well tested today, and the gravitational redshift occurs as light loses energy as it emerges out of a gravitational field. These are the classic tests of general relativity. There are more modern tests involving recent observations of gravitational waves from merging black holes. And these are the end stages of gravitational collapse. So, your space time gets more and more curved depending on the mass of the object. If it is a white dwarf or a neutron star, the gravitational field is strong. If it is a black hole, there is a very strong the space time itself is ripped off in some manner, and you have a very strong gravitational field very close to the center of the black hole. And what happens is that the light cones around massive objects begin tipping. If you have a star, this is the space-time diagram of a star with one dimension suppressed. This is time, and these are the two directions of space, and far away the space-time is Minkowskian. So, the light cones behave in the same manner as they do in Minkowski space-time. As you come closer to the star, the gravitational field is higher, and the light cones start tipping towards the central object. And if you have a black hole, you have here a collapsing star which eventually forms something called an event horizon, and the event horizon is essentially the location where the light cone has tipped completely. Therefore, a future trajectory is towards the center of the black hole. And if you have a static object, if you have a completely spherically symmetric collapse, then this essentially corresponds to the Schwarzschild radius, which is given by 2 gm in c equal 1 units, and this forms the event horizon of a black hole. And what had happened in the late 60s was people were trying to understand properties of black holes, and they had come up with and they had noticed this interesting property which goes by the name of area theorem, which essentially states that the area of a black hole never decreases. So, what it means is that if there are two if you have a single black hole, it can accrete mass, and it can its area can increase. If you have more than one black hole, and if they merge, the area of the eventual black hole has to be at least greater than or equal to the sum of the areas of the two original black holes. In some sense, it behaves like this the entropy of a thermodynamic system. As you know, the second law of thermodynamics states that the delta S, the change in the entropy, should be greater than or equal to 0. And many such properties of the black holes led to the formation of the so called laws of black hole thermodynamics. Zeroth law is what describes equilibrium of an object at a finite temperature, and what one finds is that the surface gravity of the black hole, in some sense, this is the acceleration due to gravity in the Newtonian sense calculated on the horizon, and this happens to be constant for a stationary black hole. And this is reminiscent of thermodynamics, wherein a system in thermal equilibrium has the same temperature everywhere. And this is in some sense related to the Unruh effect that we talked about earlier. We had seen if an object has if an observer has a certain acceleration, there is a temperature that can be attributed to it. I mean, the observer may see the vacuum state to be thermally populated with a temperature proportional to the acceleration, and we will see the temperature of the black hole, we will talk about it in due course when we discuss Hawking radiation, is indeed proportional to the surface gravity kappa. So, in that sense there is a close relation between Unruh effect and Hawking radiation. There are so few subtle points I can discuss in person. And there is also a first law. Notice this is the change in the mass of the black hole, dm on the left hand side. This is angular momentum, this is charge, etc. So, for instance, dA, kappa is like the temperature, and we have already discussed as to how the area behaves like the entropy. This is, for instance, like dE is TdS plus possibly PdV, and there can be different kinds of work that can arise. So, this is like the first law of thermodynamics, and second law, as I already mentioned, in a manner similar to the thermodynamic entropy, the area of the event horizon never decreases. And the last third law, we do not require it, but nevertheless let me state it here. The surface gravity of a black hole horizon cannot be reduced to 0 in a finite number of steps. What it means is that the temperature cannot be completely made to 0 in a small number of steps. So, now these were the classical laws of black hole thermodynamics, and no one thought, in the classical sense, black holes are black, perfectly black, and no one thought anything can emerge from the black hole. And this is where Bekenstein comes in, and famously John Wheeler had asked Bekenstein whether one can violate the second law of thermodynamics. You have a cup of tea and I throw it in the black hole. Can I violate the second law of thermodynamics by hiding everything inside a black hole? And what Bekenstein did was propose this so called generalized second law of thermodynamics, which states that the sum of the entropy of the black hole, I cannot violate the second law, but I just have to modify my second law suitably, because black holes also carry entropy. When I take T, it has a certain energy or mass, and I throw it into a black hole, it changes the mass of the black hole. The mass determines the area changes, therefore the entropy changes. So, he said that the entropy of objects outside plus the area of the black hole, that total entropy, the change in that should be greater than or equal to 0, and this is known as the generalized law of black hole thermodynamics. But we have this peculiar situation that black holes have entropy, but they do not seem to have temperature associated with it. And another point is that entropy, we said that area behaves like entropy, but area is a dimension full quantity, entropy is not. How are we going to relate them? And this is, this is where the challenge is, and this is where Hawking comes in. And what he did was that until then people were essentially studying classical fields, behavior of classical fields around black holes. Hawking chose to study quantum fields around black holes, and that is where the black hole physics comes in this elements of semi-classical gravity, wherein we are discussing behavior of quantum fields in classical backgrounds. And in a manner similar to the Schwinger effect that we discussed, what can happen is the following. Here you have a black hole, right? This is the black hole event horizon, this is the singularity that is at the center of the black hole. And as we already discussed, there will be virtual pairs of particles present everywhere. And you can imagine a situation where there is a pair of particles, they can emerge and annihilate and disappear, nothing will happen. On the other hand, some of them can one can fall into the black hole, one part of a pair can fall into the black hole and the other can emerge to infinity. This is a rough picture of what Hawking radiation is, and it is a reasonable picture, and I will try to provide a more clearer picture as we go along. What essentially happens is as follows. Here we had considered a static black hole. Remember, we have been studying the evolution of quantum fields in a gravitational background, and we had seen that if you have a completely static situation, the modes will not change. A positive frequency mode will remain a positive frequency mode, right. So, if you have a static situation, a black hole which is a black hole forever, it may not produce particles. But black holes are not formed, just like that. They occur due to collapse, and it is the dynamics during collapse that introduces this time evolution, and that is what this picture illustrates. So what we have is this guy here, right, is this guy, is the surface of the star, which is collapsed into a singularity, and this line here is the event horizon. Okay? So you can think of what is happening is that you have the spherical shell which is collapsing. Modes, if you had a completely static situation, right, and think of a scalar field which can pierce through the black hole or whatever matter that is present and come out to the other side. If you had a static situation, as you come in, there will be a certain amount of redshift of the modes, I am sorry, blue shift, because you are going in, and as you emerge there will be a certain amount of redshift because the modes are emerging out of the gravitational field. Think of a pure classical mode, and the extent of redshift and blue shift will be the same if it was completely static, but not so when it is dynamical. The object has collapsed, right, is collapsing to be precise, and there will be a difference in the behavior of the frequency of the modes as they come in and as they go out. And what you find is that, notice here, you have various modes that are coming in. I am assuming that some of you are familiar with this idea of Penrose diagram, which I will have to use later. This corresponds to scry minus, which is past null infinity from which the modes are coming in, and that is what these modes are. If the event horizon has not formed, this will go to, they come from past null infinity and they will emerge, go to future null infinity. For simplicity, I am going to consider massless field, so they will follow null rays, but the null rays are bent because of the gravitational field. But what will happen? Notice what is gamma here. This is useful, this is important to appreciate when I discuss the a simple derivation of the Hawking radiation. Notice what is gamma. Gamma is the ray that eventually hugs the event horizon. Any ray that is incoming after gamma, what does it do? It just falls into the black hole, it hits the singularity, never emerges. Now this is the collapsing shell. Now what one needs to do is very simple. You have an incoming mode, you have an outgoing mode. You need to understand what is the Bogoliubov transformation. Evidently there is a change because of it is going around in the field of a collapsing shell. All you need to do is obtain the relation between the ingoing modes and the outgoing modes, ingoing modes at early times and the outgoing modes at late times. Because there is a time dependence, there will be a non-trivial Bogoliubov transformation that relates the very early and very late times. And what you find is that there is an exponential redshifting of the modes, and it is this exponential redshifting which leads to a beta whose mod squared gives a thermal spectrum. This is not difficult to understand, and that is why it is closely related to the Unruh effect. I will come to that in a minute. I will just make a few remarks about this. So as I have said, modes that skim the event horizon as it form exhibit exponential redshift because they are the closest to the horizon, which is responsible for the thermal nature of the particles. I will explicitly illustrate this with the help of the example of the uniformly accelerated observer. And there is a thermal spectrum, and I think I have missed an m here in this expression here. There has to be an m, okay, in the denominator, all right. and it is the temperature is inversely proportional to the mass, and you can put in the numbers and you find that a mass, a black hole with a solar mass will have a temperature of about 10 power minus 8 Kelvin. It is extremely small, and that is the challenge to detect this Hawking radiation. So, let me just highlight what happens to exponentials. I have to go quite a few slides back to the case of the Unruh effect. Notice the relationship between the t and eta. Remember, eta is the proper time in the frame of the uniformly accelerated observer. Now, remember your mode, Minkowski mode. What will happen? It will be of the form e power minus I omega t minus k dot x, all right. And let us say you have a right moving mode. So, what will happen is that you will have something like t minus x. Okay. Notice what is t minus x. There will be a e power g xi times some exponential, because it is sine hyperbolic g minus cos hyperbolic g, which will give you an exponential. So, in other words, the phase of your Minkowski mode in the frame of a uniformly accelerated observer in his proper time has an exponential. So, in other words, you will have e power I times some constant times e power g eta. You can ask the simple thing, right? I have a plane wave which will be of the form e power I omega t minus x, a right moving wave, and there is an observer who is moving with a uniform acceleration. I can ask, what is the Fourier transform of the wave in the frame of the observer? So, what will I do? I will just Fourier transform this into his frame. In some sense, that is what we did when we discussed this. You substituted this trajectory in the Whiteman function and Fourier transform, and if you notice, you had some gamma functions which squares gives you the thermal spectrum. It is exactly what happens. The outgoing mode is related, frequency of the outgoing mode is related in an exponential fashion to the ingoing mode. And because of this reason, when you try to relate the outgoing mode to the ingoing mode, okay, you will have a gamma like this, a gamma function whose square will lead you to a sine hyperbolic, and there is an exponential, and that will eventually lead to the thermal spectrum. A simple exercise to carry out is what I just described. What is the frequency distribution of a plane wave in a uniformly accelerated observer? And that happens to have a thermal distribution. I will come back to Hawking radiation. There is a nice simple way of understanding Hawking radiation, and this is with the help of the moving mirror model that I have already introduced you to. So, now consider a mirror trajectory. Earlier we had considered an arbitrary trajectory. Let us consider a specific trajectory where it is static at very early times, as we had discussed in the previous lecture, and it accelerates asymptotically. Notice this, as t tends to infinity, right, what happens is that t minus t plus z, if you take this to the left hand side, t plus z becomes b. In other words, v becomes b. So, what will happen? Modes which have, for v equal to b will just scrape the surface of the mirror. Modes which come in later with v greater than b will never hit the mirror. So, there is a last mode gamma which scrapes the mirror, and beyond that it does not hit the mirror at all, and it closely resembles this gamma here. Okay? All right. modes beyond that will just go in. And you can, what you can do is that you can ask what is the Bogoliubov coefficient. You have some in vacua, which is where we use the, we had calculated the stress energy tensor, for instance, and you can ask what is the relation between the in vacua and the vacua or the modes at late times, and you can calculate the Bogoliubov coefficient, and what you will find is that, and you can ask what is the number of particles produced by this moving mirror. And notice there is only one quantity which is present here, which is kappa, which essentially describes the acceleration of the mirror at late times, and you will find that beta squared is a thermal spectrum with a temperature which is proportional to kappa. And in fact, if you compare the behavior of the modes in the original Hawking paper and this example, they are exactly identical. And it is this exponential behavior in the trajectory of the mirror and which leads to the thermal spectrum that is encountered in this case. And this is exactly what is mimicked in the context of Hawking radiation. So, this sort of completes this puzzle that had remained in black hole thermodynamics. Now, you can ask what is the entropy associated with it, and what is the temperature associated with it, and everything fits in the expected laws of black hole thermodynamics. And importantly, we have a temperature, but it is just a quantum phenomena, and that is why you have an h bar which appears. You cannot construct a quantity which has dimensions of temperature without the h bar thrown in, and that is why Hawking radiation is a completely quantum phenomena. And there was one more puzzle which is not relevant for our story, but it is not difficult to construct. Remember, we had the other quantity which was the entropy, which was proportional to the area, which is a dimensionless quantity, I am sorry, which is a dimensionful quantity. Entropy is a dimensionless quantity. So, we need to divide the area by some suitable quantity, and this happens to be a Planck length, squared of the Planck length, of course. That is the only fundamental quantity which you have in terms of h bar, c and g, and in some sense a black hole entropy is the number of possible ways you can arrange the area in terms of Planck length. And black holes evaporate, and notice what happens is that the temperature, the Hawking temperature, is inversely proportional to the mass, and therefore, as the black hole is evaporating, its mass keeps decreasing, and therefore, at later and later times the evaporation grows higher and higher, and in fact they are supposed to explode. And if you are studying formation of primordial black holes during inflation or something, there is a strong constraint about what type of black holes will remain because of the lifetime of black holes from Hawking radiation. If they are if they have a small mass, they will last. Their temperature is larger, and therefore they will evaporate faster. The larger the mass, the slower the temperature, and they will last longer. And as I just mentioned, you can attribute an entropy to the black hole, and all you do is that you count in terms of the so called Planck length, area in terms of Planck length, and that determines the entropy of the black hole. So, that completes the discussion about the thermodynamics of black holes. In the next part, I am going to talk about possible imprints of Planck scale physics. I already narrated this story, and I will explain with the help of this so called conformal or Penrose diagram. This is supposed to describe a black hole. Okay. So, what do you have? This is the surface of the collapsing star, which has eventually formed, gone into the horizon, and this is what we refer to as Scri minus. This corresponds to in what is known as past null infinity. This is future null infinity. This is the singularity of the black hole, and this is the center of the black hole. For instance, this is r greater than 0 is, and therefore you have only this domain. This corresponds to just simply very early times, and this corresponds to very late times, for instance, and this corresponds to spatial infinity. So, this is the surface of the collapsing shell which has gone on to form the black hole, and we are considering massless modes, and therefore modes travel along null rays and come out. The Penrose diagram is constructed in such a manner such that the light rays will always travel at 45 degrees. So, they go at 45 degrees. And what do? You impose the initial conditions on the modes at very early times here. Remember, the shell is large, okay, and therefore, the gravitational field outside is weak, and therefore, it is like Minkowski vacuum. It is very similar to the fact that when we are carrying out LHC experiments, we work with the Minkowski vacuum, though there is a gravitational field present, because the gravitational field is rather weak. As the shell collapses, modes go in, come out, and at late times is when you observe Hawking radiation. That is the Bogoliubov transformation, Bogoliubov coefficient relating the modes on Scri minus and Scri plus and Scri minus. They, mod squared of that, will have the thermal spectrum that I have been talking about. Now, what one finds is the following. As you track back the frequency of the modes, if you ask what is the wavelength of a typical mode constitutes Hawking radiation here, and ask what is its frequency when you had imposed the initial conditions on the field, its frequency is very high, okay, higher than the Planck energy, or in terms of wavelength, its wavelength is smaller than the Planck length. And this leads to the question whether Planck scale physics can affect Hawking radiation. And similar thing happens in inflation. Let me remind you very quickly what happens during inflation. What has been plotted is a picture that you will all be familiar with. I have plotted the logarithm of a length scale against the logarithm of the scale factor, which is essentially the E-fold. You have radiation dominated epoch here, and you have inflation here, and there are two quantities that have been plotted. One is the wavelength of the perturbations, and what you do when you carry out, say, linear perturbation theory, cosmological perturbation theory, is that since you are working in the linear regime, modes evolve differently, different Fourier modes evolve differently, and when we talk about a wavelength of the perturbation, we talk about these different modes. And the physical wavelength in a Friedmann universe is always proportional to the scale factor, and they have, in this log-log plot, have a slope of unity. The blue line is the Hubble length, okay, or the Hubble radius, and in radiation dominated epoch, you can easily show that the Hubble radius, which is 1 over h, behaves as a squared. Therefore, in this log-log plot, it has a slope of 2. And if you have something like slow roll inflation very close to d zeta, h is almost a constant, therefore, dh is a constant. And as you track back some cosmological scales to early times, all you need to make sure is that these modes are inside the Hubble radius, and if they are inside the Hubble radius, if you have learned some perturbation theory, as we will also soon discuss in the context of d zeta, you can impose well motivated Minkowski like initial conditions and evolve the perturbations. And so, how do you evolve these perturbations? How do you calculate the perturbation spectrum? And I will illustrate this with the help of a simple d zeta example. Scalar and tensor perturbations in the early universe can be modeled by a massless scalar field, let us say phi. This is not a very accurate statement, but this is true, for instance, if you consider power law inflation. In d zeta, this is true. Actually, it is true in any background for as far as the tensor perturbations are concerned. Scalar perturbations are involve a little more detail because they depend on the form of the potential. So, let us for simplicity consider a scalar field, massless scalar field, evolving in a Friedman universe. We have already encountered the equation of motion of such a field in a Friedman universe, just that we are going to work in 3 dimensions rather than 1 plus 1 dimensions. And it is a real scalar field, and therefore, I can decompose in this fashion, where A k is some annihilation operator and mu k by A is just a convenient way of decomposing my scalar field, nothing more. And k is of course mod k, and because of the homogeneity, I can decompose the normal modes as e power I k dot x. And what one finds is that the modes mu k satisfy this differential equation, and these primes are the primes with respect to the conformal time coordinate. I think I should just take a minute to explain what I mean by the conformal time coordinate. We had discussed this example in the in the previous lecture. Here we had a massive field, and in 1 plus 1 dimension, something mass, the field is conformally coupled, not so in 3 plus 1 dimensions. So this eta that I am talking about later is this conformal time coordinate. This decomposition, I am sorry, this transformation from t to eta can be carried out whether you are working in 1 plus 1 or 3 plus 1 dimensions. So now what I have is a massless scalar field, but in 3 plus 1 dimensions. So that is what I have. So I substitute in the wave equation and I get a differential equation such as this, where the primes now denote differentiation with respect to this conformal time coordinate eta. And the spectrum associated with the perturbations or with the scalar field here is defined in this fashion. It is again dependent on the 2-point function. This is the Whiteman function which we have encountered earlier. The Whiteman function is here evaluated at the same point in space and time in some manner. It will be divergent, but we do not need to worry about it, because we have introduced this integral on the left will be divergent, but that is not what we are interested in. We are interested in without the integral, this quantity which we define as the power spectrum. And this expectation value is evaluated in some state which is annihilated by the annihilation operator for all k, of course. So what you do is that you take this expression, this decomposition in this expression, and you can arrive at this power spectrum. So what you are supposed to do is that given an A of eta, some Friedman model, you plug this in, you solve this differential equation. There has to be some initial conditions that have to be imposed. Since inflation is supposed to overcome the horizon problem, you impose initial conditions when the modes are well inside the Hubble radius, and evolve those modes and evaluate the power spectrum. What you will find is that this mu by A depends on time. It explicitly depends on time. But what one can show is the following: you impose the initial conditions here when the modes are well inside the Hubble radius, you evolve them, and it is a fairly generic property in inflation that if you evolve these modes outside the Hubble radius, their amplitude become constant. So this amplitude will become constant once the modes leave the Hubble radius, and it does not matter where you evaluate, whether at the Hubble exit or at later times, the amplitude of the power spectrum will differ only by a small factor. So we will focus on Dct inflation, which corresponds to A being 1 over h eta, where h is a constant. So you can go back and plug A in this, then you will have 2 by eta squared. This is trivial to solve, and the modes are given by this expression. Evidently, there has been a choice that has been made about the initial conditions, and that is not difficult to understand. You want to impose the initial conditions when the modes are well inside the Hubble radius here, and that essentially corresponds to k eta being very large. At very early times, all the modes are inside the Hubble radius if you have eternal inflation, if you have inflation lasting for a long time. When k eta is very large, notice this vanishes, you are left with e power minus I k eta, which is your positive frequency mode. And I can define this vacuum state, I choose my mode to be that. At very early times, it is like e power minus I omega t. It is not just t, it is eta now. And I define this state to be the coefficient of this, to be annihilated by the annihilation operator, which is the coefficient of this mode. And such a vacuum state is known as the Bunch-Davies vacuum. Now, what do you need to do? You need to evaluate the power spectrum on the super Hubble scales when the modes are well outside the Hubble radius. That is again corresponds to the case very late times. Remember, Dct inflation goes from eta equal to minus infinity to 0. Okay. So, it corresponds to eta equal to 0. So, what happens is that this is the phase factor goes away and you will essentially have 1 over root 2 k. So, when I square it, I will have 1 over and eta goes to 0, I am sorry, this will go away and you will have this term present in comparison to that. So, you will have 1 over k power 3 by 2 arising out of mu by a. Okay. A I do not care because it is independent of k. There is a k cube, mu k by a gives me 1 over k power 3 by 2. When I square it, I get k cube goes away and I will be left with a constant. And that constant happens to be h by 2 pi whole square. And this is the power spectrum. In fact, this is exactly the power spectrum modulo factors associated with the various degrees of freedom corresponding gravitational waves. This is exactly the power spectrum associated with the gravitational waves in Dct inflation. Now, the question is, do Planck scale physics alter this power spectrum, and is there some way we can understand how they may alter this power spectrum? I have repeatedly mentioned how, as you trace back the modes, a wavelength today, some wavelengths today to the early stages of inflation, they can become sub-Planckian in length scales, and this illustrates, this slide illustrates this, gives you the numbers for that. So, we are assuming some typical values for the inflationary parameters. I am assuming Dct inflation corresponding to h of about 10 power 14 GeV. Inflation is supposed to have occurred at about 10 power minus 35 seconds and there are 70 e folds of inflation. Evidently, these numbers will shift slightly as you change these numbers, but certain modes will be sub-Planckian at early times. So, what is this? This traces back a lambda naught, which is the wavelength of a perturbation today to the end of inflation, and that is given by this expression. That is roughly like 10 power 14 GeV divided by about 10 power minus 4 eV, which corresponds to the temperature today. And then you track back that mode from the end of inflation to the early stages of inflation by a factor of 10 power 70, and you get this number. So, the lambda today is related to the lambda at 70 e folds before the end of inflation by a factor of 10 power minus 58, which means if you work with something like 2 megaparsec today, which is borderline cosmological scale, you will find that it is like 10 power minus 34 meter. So, in other words, length scales that are of cosmological interest today would have been smaller than the Planck length during the early stages of inflation. So, this raises the question as to whether Planck scale physics will modify your primordial perturbation spectra, and this is known as the trans-Planckian problem in inflation. How do we go about that? Well, the idea is fairly simple. What does this mean? Let us understand it from this picture. The first thing is that we do not have a theory of quantum gravity, which means that I do not know how the dynamics will be changed when the modes are sub-Planckian in wavelength. You can construct some dynamics, it is non-trivial, and it will be ad hoc because we do not have a working quantum theory of gravity. What was suggested was simple and nice. There is some ambiguity. It's as follows. Notice as you track back the mode, if I draw a horizontal length here, right, it corresponds to a fixed length. If I draw a horizontal line, it corresponds to a fixed length. Let me draw a line which corresponds to the Planck scale. It will be somewhere like this, right. If this corresponds to 2 megaparsec, right, somewhere here would be Planck scale, right, and therefore, I will draw a length much in, Planck scale will be smaller, earlier and earlier it will be, smaller and smaller scales would be inside the Planck length. It will be like this. If I draw a line like this, what will happen is that it is clear that different scales will emerge out of the Planck length at different times. You understand? What do we do now? We impose the initial conditions in standard inflation on all the modes at the same time, which is very early times. But they are, they are roughly at the same time correspond to the modes of cosmological interest. You are imposing as eta tends to minus infinity. Instead, what I am going to do is that I do not know, below this scale, the dynamics of the field I do not have a feel for. I do not have an understanding of what happens there. Therefore, I am just going to impose a non-trivial initial condition as the modes emerge from the Planck scale. You understand? But the thing is, I cannot impose the initial condition at the same time, because different modes come out of the Planck scale at different times. This is very similar to what happens corresponding to Hubble exit. Not all modes leave the Hubble radius. Hubble radius in d zeta is fixed. All modes do not leave the Hubble radius at the same time, they leave at different scales, at different times. In the same manner, if I draw another horizontal line which corresponds to the Planck length, they will emerge out of the Planck length at different times. So, I do not know the dynamics, what happens prior to the time when they were inside the Planck length, but as they emerge from the Planck length, I will impose some initial conditions. And you know that the most general solution for my perturbation equation is this guy, right. It is alpha u plus beta u. Instead of alpha and beta, I have called them A and K, A and B, and you know that A squared minus B squared is 1. That is just the Wronskian condition for this mode. Now, what is left to you is just a choice of what the initial condition has to be as the modes leave the Hubble radius. There is some ambiguity here, and the simplest is to assume, right, if you have nice oscillatory behavior, right, the conjugate momentum which is like phi dot or phi prime is I k times my original mode. This is one of the simplest conditions I can impose. Okay. In some sense, this satisfies the minimum uncertainty in mu and pi in some sense as they leave this Planck scale. And this was proposed, and as I said, it has to be imposed at a certain time where capital M is my new scale, new mass or energy scale. And I impose that initial condition when this is satisfied. Notice this k eta is, this just corresponds to the time eta naught when this scale k emerges out of M inverse. And I impose this initial condition on these modes, and that determines A and B completely. Actually, it obtains gives me a relation between A and B, and this relation between A and B fixes it completely, modulo phase factors which I do not care about. And you can ask what is the corresponding power spectrum, and that happens to be this. And there are a few lessons to learn from this. First, in d zeta, notice we are interested in asking whether there is a change to the power spectrum. In d zeta, the power spectrum is strictly scale invariant, it is flat, there is just an amplitude, nothing more. Now, what this has done is that it has just changed the amplitude, there is no k dependence here. This is a peculiar aspect of d zeta inflation. Whatever you do, it will be scale independent. Now, you can carry out this exercise in power law inflation and understand what the scale dependence is. What will happen is that you will get your, this is my original spectrum in the absence of Planck scale corrections, and what is important is that notice the Planck scale correction, it is h by m. And what is h by m? If you use the constraints on the tensor to scalar ratio, if m is the Planck scale, h by m is like 10 power minus 5 or so. So, this is possibly, if your corrections to the power spectrum is of the order of 10 power minus 5, they can leave. For instance, what if you repeat this exercise in power law inflation, what it does is that it introduces oscillations in the power spectrum. And you can check whether they are consistent with the data, you can run MCMC and examine how well they fit. Unfortunately, the oscillations have to be reasonably large in order to improve the fit to the data, and therefore, whether they are Planck scale corrections is, is not clear. But here is one way of actually confronting possible Planck scale physics with observations. Now, what happens in the context of black holes? Will Hawking radiation be modified? It is clear here, you expect some corrections, the corrections of the order of h by m or maybe some power of h by m. These are the only two scales that you are left with here. What are the scales you have in the context of black holes? You have the Planck length and you have the Schwarzschild radius. Here they differ by 10 power minus 5 or so, that is h by m, I should be careful, h by m is 10 power minus 5 or so. If you take a Schwarzschild radius of mass of a sun, which is a few meters, few kilometers, right, versus the Planck length, that ratio is incredibly small. And therefore, it is often believed that the corrections to Hawking radiations are considered to be much smaller than, and such Planck scale effects, if you are going to observe, they are possibly observed in primordial spectra, provided they are of the order of h by m Planck. If they turn out to be h by m Planck squared, which some arguments lead to, you are unlikely to observe them. So, that sort of concludes various things I wanted to say in these 3 lectures. So, I will just quickly summarize with a few remarks. In these lectures, I have discussed the following phenomena that occur when one examines the behavior of quantum fields in classical electromagnetic and gravitational backgrounds. I discussed the Casimir and the Unruh effects in my first lecture. I discussed the Schwinger effect in my second lecture, and I talked about Hawking radiation, which is again a particle production phenomena very much like the Schwinger effect, and I talked about how black hole thermodynamics in some sense was responsible for the discovery of Hawking radiation, and towards the very end I talked about how there can possibly be some Planck scale modification to semi-classical effects, and these may be understood with the help of simple models. Just a few references, there are some classic textbooks which discuss many of the phenomena that I have discussed. Birrell and Davis is good old and classic text. Fulling is more mathematical and it is also a good old text. Wall discusses black hole thermodynamics in his monograph, and there is a more modern text which discusses many of this physics, which is by Mukhnov and Vinitsky. With those remarks, I will stop here. Thank you.